All right. Hello, everyone. Happy remote learning day with all the rain. How's it going? I almost forgot to turn on my sound this time, but fortunately, I remembered just now. It feels so good to have a haircut. I have been procrastinating on the haircut front for a long time, as you can see, and I just feel like a new person. I got a haircut yesterday. It's great. So yeah, with all of the rain today, it just makes me pretty happy that we're able to make use of the remote learning environment for a little bit of benefit here. And I hope that you guys are appreciating that as well. Hope that your other classes are going okay. And I hope that this class is going all right for you. And a quick update about the exam. I have started grading them. I've gotten through a few, not as many as I would have liked, but I'm working through them. So I'm working on that process, and I will see if I can get them back to you for Thursday. But I'm not sure yet if I can manage that. Let's see, homework. I will post this week your final homework assignment. I'm also planning to post some participation activities. I know I have not posted any in a while. I apologize for that. I have also not gone through and graded or tabulated your prior ones. I will do that soon as well, probably this week. So logistics wise, I'm just a little behind on stuff, so I'm going to try to catch up this week. If there are any specific pressing concerns, let me know. But I am planning to do some catch up on that, get you the assignments you need and the activities this week. So I'll send out an email announcement when I do post these things as a reminder. With that, I wanted to take a quick look with you over our syllabus and just kind of to make a note. It looks like, according to the last draft of the syllabus, I was thinking maybe we'll do a lecture on membrane bioreactors, but last time instead we went over the exam. That would have normally pushed the membrane bioreactors to today, but I prepared for BOD. So what I'm going to do is I'm going to switch the membrane bioreactors, probably swap it with the nutrient removal and residuals, or I might just touch on both on that time. So we'll see kind of what, maybe if you guys give me any feedback that you'd like to see one or the other, or we'll kind of see which one I feel like I can give a more interesting lecture on. That, whatever topic that'll be, is really not going to be covered directly in kind of quantitative manner on the exam. We might touch on the topic or something, but it's not going to be any real new core material for the class. Both topics I think are fairly interesting. So anyway, that's the plan. Today we're going to really take a look at biological oxygen demand. We've used it as a term a lot so far this semester, but we have not yet really talked about how we define it, how we measure it, and how to work with it. So the reason I decided to delay that part and teach on the wastewater part first was because I think it makes sense to look at the wastewater treatment and then to consider, okay, well, what happens after wastewater when we discharge water into the environment, to kind of make that complete loop in terms of how we are considering the amount of waste we're putting into the environment and how we treat it, and why our regulations are set up in the way they are. So from here, basically till the end of our class this semester, it's going to be about understanding what happens downstream of the wastewater, specifically of secondary wastewater treatment. Okay, so with that, I'm going to get into it. But again, hello for everybody tuning in now. Let me know how you're doing. Would you guys like to, for me to set up some sort of a poll or feedback to give me some feedback about how the class has been, suggestions for improvement? Theoretically, in the future, I'll go, we'll be back in person, but one of my own goals is to keep some of this aspect in terms of live streaming and allowing students to watch the lectures later or catch up on materials in this manner. So if you have any feedback, I'd love to hear it. In the beginning, it took me a long time to set up, or a longer time to set up material in this way, but once I have it, now that I have it, I think I can do it pretty effectively. Now, I don't think I can bring in the fish cam for my live lectures in person, but aside from that, I think I can hopefully deliver hybrid mode in the future. And I think that would help, even like if this was a normal semester, normal time, no pandemic or whatever. I think that would help everybody. So, would you like some way to give me feedback? Are you listening? You're just eating lunch? Tell me how it's going for you. And on that note, LSU is going to be posting the course feedback soon, and so as always, I really appreciate your honest feedback, constructive criticism where it's needed, and just let the system. Some administrators may look at this. I look at my feedback that you give. It's all anonymized. So let me know how you're feeling in that regard. Okay, a poll could work. Just got the email. Okay, so thank you. What my plan then is going to be, I will move this out of the way so you guys can read. I'll make a poll for next time, and I'm going to write that down real quick. So hopefully I remember. To get some feedback about the course, any thoughts you have. And then please also do, and that'll be a live activity, probably Kahoot or something, to get those of you who are currently watching your thoughts on some things. But then please also do fill out the course evaluation. I love it when students put comments. Sometimes it's just pure entertainment. I occasionally will get a bitter student who really had a negative experience, and it's I feel bad to the extent that it's my fault, but as is true with probably any instructor-student relationship, some part is the instructor and some part is the student. So sometimes it's a case where it's very clear that somebody's complaining because they didn't do enough work. That's always amusing. But more than that, I really do appreciate anytime somebody gives me feedback, even if it's critical, especially if it can help me improve the course for future years. Even if you're just saying thanks or laughing at the Fatberg flushable wipe situations. So whatever you find was particularly useful, interesting, helpful from this course. I know a lot of you are civil students who don't really care about environmental engineering necessarily, in terms of you weren't planning to work in this area. So from that perspective, I'd love to hear about the experience, since you have to take this and you weren't looking forward to it necessarily, or if you're a chemical engineer and you're taking the course, it's an option, and you're interested in this type of topic, but from the chemical engineering perspective, your feedback, whatever the case, I really appreciate hearing how your experience has been. Okay, so with that, I'll get into our lecture for today. Kind of care. Awesome. I'm glad to hear that, and I know, that's not a very good. That's not very fair of me, because I do know a lot of the civil students have expressed interest and engaged in the class, and there's always a good fraction of the civil students who really actually care, partly just about learning, or about environmental issues, care about the classes that you're paying to take, and so it's unfair of me to say that you don't care. Very true. But I also know that in the past, there have always been some complaints about the chemistry or different things from some students. Okay, so at least I can tease you guys because I took a different route with my education and never took civil classes, so I feel like I can poke fun. Anyway, so biological oxygen demand, or you can call it biochemical oxygen demand. We did talk about it, and we did learn a bit about it in terms of what it means. And so just to recap, it's really biodegradable matter or stuff. And I'm going to, I need to bring up my pen tool again, so 1 second. So BOD, biological oxygen demand, it's biodegradable stuff. There we go. And so the biodegradable stuff is that microbe food. We can just kind of describe it as random dissolved organic compounds. And essentially what's going to happen is as the microbes eat it, they're going to consume oxygen. That's where the oxygen demand comes in. They're going to form CO2. That's where the oxygen goes. That's like us breathing in and then breathing out. We are demanding oxygen from our environment. And if you were to be in a confined space and there's a limited amount of oxygen, you can deplete the oxygen to an extent. Same is true for water. If microbes consume all the oxygen because there's so much food, then they will deplete the oxygen. That's why we care about it. And they're going to be eating it to make new cells, to do whatever microbes do. Now, there are several types of oxygen demand we can consider, and one of them would be theoretical oxygen demand. That's the theoretical limit in terms of a chemical analysis that a compound or some chemical can exert. And so that's really looking at it in terms of a stoichiometric analysis. Like, for example, glucose. If we have C6H12O6, then we could consider what it would say, what it would look like if we had some amount of glucose and we're going to consume some amount of oxygen to form, in this case, it should be 6 CO2s, or we'll start there anyway, start with the balance on carbon. And usually we'll have water as the other byproduct. Maybe there's some other stuff, but again, in the theoretical sense, if we were to completely oxidize this stuff, or some people would call it mineralize, if we mineralize glucose, you can think of that mineralization as if we've got a campfire and we're burning it and it's turning into ash. That ash is essentially the mineral form of whatever that you burned that was not volatile, that was not released as gas. CO2 as a gas, water vapor as a gas, nitrogen gas, whatever was burned but did not volatilize. So let's say you have a little bit of calcium in the wood, or a bit of, phosphate or something, phosphorus, that will turn into phosphate, that'll be part of your ash. This is one reason why ash is sometimes a good thing to add to soils for kind of enriching the nutrients, is because you have the mineral leftovers of plants probably have a lot of the micronutrients that they need. So we have C6H12O6 plus some amount of oxygen going to water. So let's just start with 1 glucose. We have 6 CO2s, and let's balance the hydrogens next. So we've got 12 over here. That means we need 6 waters to balance that. And now we look at the oxygen. We have 6, we have 12, we have 18 total on this side, 18 oxygens. So we need 18 on the left. Well, we have 6. That means we need 12 over here. So that'll be 6 oxygen molecules to make 6 CO2 molecules and 6 water molecules. So to oxidize 1 molecule of glucose completely, we need 6 molecules of O2. So that's the theoretical oxygen demand, right? In practice, microbes are not that efficient, and the organic compounds are not that simple. So in practice, we're not going to get that theoretical. So we see that the theoretical is going to show us the very most oxygen that, for example, glucose could demand from water or the air, if that was the case. The next type of oxygen demand we can look at is chemical oxygen demand. Now, a chemical oxygen demand, or COD, this is, you would think that that's, you hear the word chemical and you're like, oh, that should be the same as the theoretical, right? It's a stoichiometry, it's chemistry. But there's, what we mean by a chemical oxygen demand is actually not quite that. When we say chemical oxygen demand, what we're doing is we are using a chemical process. And where you're saying, okay, well, we have a theoretical, but then in reality, maybe we have a mixture of all sorts of random stuff. Like, imagine if you took your cup of coffee that you had cream and sugar and the coffee molecules all in it, and you wondered to yourself, what's the oxygen demand of this mixture? Well, if you were to take the theoretical approach, you have to say, okay, well, I added 2 grams of sugar, and that's maybe reasonable. That's a mixture of sucrose and glucose, so we can calculate that. And then we look at the cream, and you start to think, okay, well, there's some lactose in it, and and then you realize there's a bunch of different chemicals in the cream, all sorts of chemicals. And then you think to yourself, well, I can't weigh that out. I don't know how much there is. It would take me a very long time to even get a decent approximation. Not to mention the coffee, like what's coming out of the coffee beans? What type of coffee beans am I using? How much did they get roasted, or how much oxidation has already occurred? Like all of these questions, and how much, it's going to be very difficult just to find the right chemicals to do that theoretical computation. So that's nonsense. That's never going to work. It's not practical. We could do it if we were just looking at the sugar there. What oxygen demand does the sugar in your coffee contribute? But it's just not practical otherwise. So, given that, we sometimes use what's called a chemical oxygen demand, which is exposing, again with a coffee example, exposing that coffee to a very harsh chemical reaction. So we take our little coffee cup full of coffee and put it in a very high temperature, add some oxidizers, like chlorine's an oxidizer, ozone, probably hydrogen peroxide, sometimes hydrogen peroxide plus ultraviolet light to get that advanced oxidation going. Some chemical system and process that is made routine. So we'll have an instrument that is analyzing, okay, we're going to oxidize everything we can by this process. And it's going to convert almost everything to carbon dioxide, to water, and to nitrogen. And again, whatever other minerals are there. So this COD then is like the theoretical, but it's actually a practical thing, right? We use it, and we determine how much organic matter, how much CO2 comes out, or really how much oxygen was consumed during that chemical process as a measurement for the amount of oxygen it demands. So we measure the amount of oxygen that is consumed by that process, and that's something we can do with a scientific instrument. So in terms of oxygen demand estimation, theoretical is going to estimate the largest when we can do it, followed by chemical, because it's a very harsh environment. And then the next one is biological. So our biological oxygen demand, we talked about, this is when we use biology to consume the organic matter, and that oxygen that is extracted from that process is essentially, we're going to have some extracted, and we're going to create CO2 and water and some new cells and maybe some stable byproducts. And you notice here there's some oxygen within a lot of these stable byproducts. So there's not all of the oxygen has been converted straight into CO2 and water or nitrogen, right? So there's still some products that could be further oxidized, is the point. And we could have consumed more oxygen to do that. So the point here is that the BOD is actually going to be a smaller estimate than the COD, which is smaller than the theoretical. So theoretically, sugar can cause a high oxygen demand. Now, in practice, an oxidation thing might not get every last sugar molecule. And in reality, with a biological system, perhaps a lot of those sugars are going into new cells, which could also be oxidized if they were then burned up or whatever. So that's kind of the scale of things. Whereas, and it's important to recognize this because we want to know how much oxygen is going to be consumed. We want to know something about our metrics here. Now, the advantage for COD is that it is a quick method that we can do in a matter of maybe an hour. We take the sample, we put it in an instrument, we calibrate it, it runs, and we then can understand, okay, given this system, given this reaction, how much oxygen was taken away. That's very nice. It's very quick, it's very convenient, and we have some good information from it. The BOD test, we have to wait for the biological process to occur. And so that's why we've seen, in many cases, BOD 5. I'll come back to that in a moment. In addition to what we see as in, let me block whatever this is. Okay. All right, so in addition to in addition to the generic biological oxygen demand that we have, that's generally what we consider carbon-based or carbonaceous. You know, a lot of the BOD that we were talking about, what we kind of think about is organic matter in terms of the amount of carbon that's converting to CO2. Technically, the COD and BOD are umbrella things, and they capture everything here, but you can subdivide it, the BOD. You can subdivide it into carbonaceous, so where it's like sugar and the carbon is being used as the energy source or the material for new cells. And you can also look at it in nitrogenous, because biological activity taking ammonia, for example, and using it, maybe incorporating that into their cells or maybe processing it. Sometimes they can use that as an energy source with a reaction with oxygen, just like you can with carbon, with organic carbon. And here you'd convert ammonia into nitrate. That process is consuming oxygen, right? So there's another way in which oxygen is demanded, not just the carbon. Okay, so given that we can take a look at the okay, I thought I had my camera too big. We can take a look at the nitrogen cycle and look at where nitrogen is being taken or is involved in the system. So not to put too much emphasis here, but it's a nice diagram about, you know, let's say plants decomposing or being eaten, and then that being excreted. We've got just organic molecules decomposing in the environment. That generally goes to ammonium first, ammonia and ammonium, and then, you know, and some bacteria can actually take nitrogen gas from the atmosphere and convert it using nitrogen fixation and kind of participate in that side of the process as well. Then we get bacteria that consume that ammonia, undergo nitrification to make nitrites. More bacteria can then nitrify that into nitrate. Plants can be assimilating it. Technically, the plants can assimilate directly from ammonia and nitrite as well. And in fact, it usually takes a little less energy from ammonia, but ammonia in too high concentrations can also burn stuff because it's caustic. So there's some considerations there why we don't necessarily apply ammonia as fertilizer, why we'd rather do it as nitrate. It's more stable, less of an issue for the plants. In some cases, maybe it makes sense to do ammonia. And then finally, you can have bacteria that take it from nitrate and send it back into nitrogen gas by denitrifying. Usually in a wastewater treatment plant circumstance, we are starting in this area and we want to give enough oxygen to at least get to here. And better yet, if we can promote the denitrification to send the nitrogen back into the atmosphere, that's the end goal. Because in addition to the oxygen demand that the nitrogen poses, it's also true that that the nitrogen released into the environment might promote growth because nitrogen sometimes is limiting. So even if it's not the food, maybe it's a nutrient that microbes need, maybe they already have enough food from just the random organic matter, soil washing down into the river from the big rainstorm we're having, whatever it may be, extra nitrogen may trigger a lot of bacterial growth in that case. Okay, so in terms of measuring BOD, a lot of the cases where we had in class, we had this little 5 here. And I didn't really make a big deal out of it. So let me explain that now. When we do a BOD test, what we want to do typically is to simply take a sample of water, put it in a bottle, seal it, usually have some sort of way to measure the oxygen content in the bottle. And then what we're going to do is monitor that oxygen concentration over time to see how much oxygen is demanded in a given amount of time. So in this sense, we have these BOD bottles, we have a known amount of oxygen that we start with inside the bottle, and then biological activity occurring for 5 days is standard. So BOD 5 meaning the oxygen that was demanded over the course of 5 days. So BOD 5 is a pretty common but arbitrary delineation. So 5 days, it's enough for a lot of biological activity to occur. Not all of it. We don't expect every last drop of food to be eaten by biology in that amount of time, but it's a pretty good amount. We almost always use these airtight 300 milliliter bottles. It's just kind of standard. You'll see them in the laboratories. You just kind of use flasks that look like this. Usually you want to use amber colored or maybe wrap them in foil because you really don't want photosynthesis. So in terms of biological activity, we just want anything that will be consuming oxygen, nothing that's going to be producing oxygen, right? Maybe there's algae in there. You don't want that. So you just keep you want to make it airtight so no oxygen can come in from the outside. You want no light so that no photosynthetic organism can produce oxygen in your system, doing kind of the reverse of what we wanted. And then we let natural biological activity occur for 5 days. Now, there's an assumption here that we will account for mathematically in that we're assuming there's bacteria inside the bottle and enough bacteria so that in that 5 days, we're not really waiting on the bacteria to grow before they can start doing their work. They need to be consuming the biological, the biodegradable stuff from the start. Another thing to consider, again, we'll handle this mathematically, is because we're going to measure the dissolved oxygen before and after in this bottle, in particular in the water that's in the bottle, one thing that we have to do is we have to make sure that we don't just consume it all and then more biological activity could happen, but we don't have enough oxygen in there. So a lot of times we have to dilute the water so that there's the right amount of waste, there's the right amount of junk, because our oxygen limits our O2 at saturation is somewhere around 10 milligrams per liter, 8 to 10. It depends a little bit on temperature and some other stuff. But if that's our overall limit to the amount of oxygen in our bottle, then we have to be able to detect some at the end. And so the other factor is the detection limit is very important. And we also keep in mind here that in a system like this, it's a very common technique, very common laboratory analysis to do. And really, we don't want to have a very ultra fancy, highly analytical instrument here. We want to be able to use a cheap, simple probe that's pretty standard and robust and trustworthy. We want something that's not so high tech, right? And so our detection limit is not perfect. It's usually something like 1 to 2 milligrams per liter of oxygen. So we really don't end up with a large amount of a large range here. We have to go from like 8 down to 2 and no more than that, because we could go down to 1 and the instrument is just reading 1, and we're just completely depleted in oxygen. We could have consumed more. That's going to give us the wrong estimation about how much oxygen demanding substrate was in there. We're not going to know how much biodegradable stuff is in our water if that's the case. So that's those are a couple of the items that we're going to cover in terms of how to estimate BOD properly. Okay, so with that in mind, our calculations here for BOD 5, we have a 5-day experiment, and we check the dissolved oxygen in the initial, and we check it in the final. So DOI is that initial dissolved oxygen, and DOF, the final dissolved oxygen. And then we have some dilution factor. So as I mentioned, a lot of times if we have high strength wastewater, then we're going to have to dilute it. Otherwise, it'll just consume all the oxygen in 5 hours, and then we need to, we're not going to have our correct estimation, especially for a 5-day experiment. So we want to dilute it, and the way we're going to dilute it is say this dilution factor is essentially the portion of water that is wastewater. So portion that is wastewater. And so given that, let's get the fish can back. Given that we have some portion that's wastewater and some portion that's the volume of a diluted water, what we're looking at is the volume of wastewater that we put into the bottle divided by the total. And in almost every case, this is going to be 300 milliliters. This is just the total volume. So V here being volume, WW being wastewater. So it's quite simple. It's just what fraction of our system, what portion of our system is wastewater, right? And so when we take a look at the BOD5 then, if we had all wastewater, that's just 1, right? The volume of wastewater divided by the total is 1, if it's all wastewater. So in that case, it would just be the dissolved oxygen initial minus the final. Literally just how much oxygen was demanded during those 5 days. Now, if we had 10% of the solution was wastewater, then this would be, the fraction would be 0.1 because that's 10%. That means we would have 1 part wastewater per 9 parts dilution water, right? Because it would be 1/10, that's 1 part waste, 9 parts dilution. So keep in mind there's some simple math here that is intuitive, but make sure you are able to understand that connection between the volumes here. It's just volume of diluted water, clean water, versus that wastewater. It's going to get a tiny bit more complex in a minute, but this is the basis, right? if we dilute it, we need to dilute it, and that changes, that's going to allow us to get into the appropriate range where this dissolved oxygen initial is something reasonable, and the final, so this needs to be like less than about 8, or rather it will be less than 8 or something, 10, 8, somewhere around there. And this guy needs to be greater than about 1 to 2 range. Okay, so as an example, we will go through a quick example here. We have a 10 milliliter sample of sewage, and we're mixing that with enough water to fill a 300 milliliter bottle. It has an initial dissolved oxygen of 9 milligrams per liter, and to help assure an accurate test, it is desirable to have at least 2 milligrams per liter drop. That's the other thing I didn't mention earlier, but in order to make sure that our measurements are valid, we need to make sure that we, if we start at 9 milligrams per liter of oxygen, and then at the end of the test we're measuring 8.8 milligrams per liter, we're really not sure if that was accurate, right? that small little drop, maybe our instrument is not accurate enough. It's kind of within that range. If we get a bigger measurement, a bigger change, then we're more confident. So what the problem is saying is we want it to go to, at most, we need 7 milligrams per liter left over. So that's our lower bounds in terms of the needing that 2 milligram per liter drop in dissolved oxygen during 5 days. It also says in the final should be at least 2 milligrams per liter. So let's say let me rewrite this and say DO final must be greater than 2.0, and it must be less than or equal to 7.0 milligrams per liter of oxygen. So that's what the problems has said so far. We're diluting sewage into a bottle, or excuse me, we're not diluting. We are putting, it says it's mixed with enough. So we're diluting sewage into a bottle to make 300 milliliters, and we have an initial dissolved oxygen of 9, and then we need 2 milligram drop and 2 milligram left over. That's our constraints. So then it asks for what range of BOD5 with this dilution produce the desired results. So what range of BOD5 is the question? So take a moment to think about that, and remember that we were defining our BOD5 equation like this. Okay. So take a moment and try that out. Let's see what you think. Does this make sense, by the way? Any questions so far? Awesome, thank you. I realize that I'm like, hey, try this, and then answer my question. not the best, maybe not the best approach. All right, so feel free to pause if you'd like, or even mute for now and come back later if you'd like to do it that way. But I'll go ahead and work through this with you here. I've got a few examples today, so there's going to be plenty of time to to look at some practice here. Okay, so for the minimum and maximum, we know something about the range that this can be, and that's going to define the range that our BOD 5 can be. And it said with this dilution. So given that it says this dilution, whatever it happens to be, that's what we're working with. So we can actually kind of assume that's constant. And so we know the initial and BOD and the dilution is just kind of, since it's not given and we're asked to compare for that particular dilution, whatever it is, we can kind of, oh wait, I'm sorry, we're given information about it. We're given that we've got 10 milliliters of water in 300. Sorry, so ignore what I was saying. So we have that dilution, so let's go ahead and solve for that. So that's one more piece here. That's going to be 10 milliliters divided by a total of 300 milliliters. We could also write that as 10 milliliters of wastewater plus, if you wanted to be very specific, 300 milliliters minus the 10, because that's going to be the volume of the dilution, is 300 minus the other stuff. That's enough water to fill a 300 milliliter bottle. So that's 10 over 300. Do that on a calculator real quick. That's 0.033. Repeating. Okay, so that's our dilution factor. So then we want to know BOD, let's say minimum, and the BOD max. And that'll be our range. And this is for a 5-day experiment, so we can go ahead and put 5 there. So the BOD minimum, at the minimum amount this can give us, or the minimum amount of BOD that can give us a result in the required range, that's going to be the case where it only dropped 2, because there's not much BOD there. It only dropped 2 milligrams per liter. So we're going to have DO initial at 9 minus DO final at the minimum amount it can drop, which is 2. So that's going to give us 7 divided by 0.033, repeating. And the max then is going to be that 9, kind of the inverse. The most it can drop is all the way down to 2 divided by 0.033, repeating. So I guess we'll just pull up Excel for this, might as well. Probably be quicker that way. So let's say we have P is equal to 1 divided by 30, which is the same thing. Then we have BOD min and BOD max. So this will be essentially, so 9 minus 7 is 2. We divide by that. So we can define that as milligrams of oxygen per liter, or really milligrams of oxygen that were demanded per liter, right? So milligrams of BOD per liter. And the max is going to be the same deal, except instead of being 2, we're dividing by, we're taking 7, right? Because it dropped 7, 9 minus 2 is 7, divided by that guy, 210. So our range then is 60 to 210 milligrams BOD per liter. And if you remember from our discussion about wastewater in general, I told you that weak wastewater is something in the order of 50, 60 milligrams per liter of BOD, and high strength wastewater might go up to about 500. So this dilution factor and these conditions are actually pretty typical for wastewater that is weak to average strength. So if you have particularly high strength wastewater, you're going to need to dilute it even more than just 10 milliliters in 300. You'd have to do 5 milliliters or maybe 1 milliliter in 300 if you had a particularly strong wastewater. Okay, so there is an added complexity here. Any issues with that, by the way? I hope that makes sense. Let me know if you did have any questions. So the added complexity in the case where we have to dilute a lot, in that case it was 10 milliliters of the waste into 300. One thing that happens is there's only so many bacteria in the waste. If we had all wastewater, the chances are there's a lot of bacteria. Just usually is in high strength wastewater. But if we dilute it so much, and the dilution water is probably, distilled water or whatever we have in the lab that's purified, then chances are good that there's pretty much no bacteria in that dilution water. So then we're faced with an issue where the few bacteria that did come in have to spend some time multiplying now that they have some food to eat, and that time multiplying is essentially a situation where they are not consuming as much as they could. If you think back to our analysis of, that wastewater microbiology, how quickly do they consume stuff? It depends on how many there are, depends on how quickly they're growing. Well, and then that lag phase, it takes some time before they are growing to a large enough extent where they're actually going to consume as much as they can to give us a reasonable BOD5 estimation or maybe a standardized. So a lot of times what we'll do is we'll add a bacteria seed. We'll add some into the dilution water. We add some bacteria and a little bit of growth stuff that the bacteria we're using to grow, because we want to add live active bacteria so that we can seed the entire volume with bacteria that will consume the waste. When we do that, we end up adding a little bit of BOD with that dilution. And of course, that's going to complicate our system because we're trying to find the BOD of the wastewater. We're trying to find the BOD of the wastewater. In order to do that accurately, we have to add a little bit more BOD because we have to add the seed bacteria. So then what we're really observing is the BOD of the mixture, and then we have to use some algebra to sort out, okay, well, what was the waste contribution if, given that we added some BOD on its side. So in reality, we have to do two experiments if we do this. We have to measure the BOD in the seed water, so we know how much BOD we're adding, and we have to measure the BOD in this mixture so that we can then use both pieces of information to find how much BOD we have in the wastewater, which is the end goal. So it's a complicating step, but once we do it, it simplifies everything. It makes it possible to perform the experiment and know how much BOD we have at the end of the day. Okay, so thinking about it this way, we have BOD5 for the mixture. This is what we observe when we make the mixture, and it's, let's say, we can think of it this way, right? We can have volume of dilution, and then I'm going to use another color and say volume of wastewater, and then we also add some volume that really it's going into the dilution, but and maybe a better way to say it will be let's do this. We have some volume of wastewater, the rest of it's dilution water, and with the dilution water, we have BOD from that dilution, from the bacteria seed stuff. So we can say, the total volume's up here. All of this is the dilution water. We have a little bit of wastewater down there, and that's going to contain some BOD of the wastewater, which is really what we're trying to find. That's what we want to know, so that we understand how much organic matter and oxygen demand our waste is contributing to the whatever water we're discharging it to. We want to make sure that's in the appropriate range. And so at the end of the day, we have the volume of the mixture, and we have a BOD of the mixture. Now, what we're going to do is then take a separate container and just use dilution water. So we'll have a secondary vessel where we have another one of these bottles. Excuse the poor drawing here. Where we have just the volume of dilution, and we're just measuring the BOD of that dilution for the whole thing. So that's going to be a separate experiment where we just do all of that, and we do both, right? So we can measure both this BOD for the dilution on its own, and then for the mixture together. Then we've got all the information we need to solve for this guy. Okay, so keep in mind our mixture is just the two added. P is the same. We can actually rearrange this if we want to and say 1 minus P is equal to the volume of dilution compared to the volume of the mixture. So the fraction that is wastewater, 1 minus that is the fraction that is dilution water. Right? That's all we're saying here. Fraction. Oops. That is dilution water. And the reason I'm writing this out is because we can simplify this equation to get a BOD5 by that term by itself, and then to simplify these other things. So if we're to take a look into the book, that's kind of what we go through. The next step, we take that equation and we say, let's divide everything by volume of the wastewater. And ultimately what we're going to rearrange for, excuse me, I misspoke a moment ago. What we want to do is rearrange for solving for the BOD of the wastewater. That's what we're looking for, right? So we actually need to get that term by itself. So that's the next few steps here. We take BOD of the wastewater, we divided everything by the volume of the wastewater, and we subtracted this guy from both sides. So subtract that from both sides. Then we have just this term on one side. Then we divide everything by volume of the wastewater, and that gets us here. So now we have BOD wastewater equals BOD of the mixture times the volume of the mixture divided by the volume of the wastewater minus this stuff divided by the volume of the wastewater. We can simplify that further, and that's where the 1 minus P comes in. So don't worry too much about it, but these are just manipulations of P, right? If we have the volumes in terms of mixture, the wastewater and dilution, chances are good we can arrange that in a version of P. That's what they're doing. So at the end of the day, they derive this equation, which you'll have on your equation sheet. BOD of the wastewater is equal to the BOD of the mixture, which that's what we measure, right? That's the before and after. That's DO initial minus final of the mixture minus the BOD of the dilution water. That's that second experiment, right? That one that we set aside, that's the dilution only. We check the dissolved oxygen in there before and after 5 days. All that multiplied, or excuse me, that term multiplied 1 minus P. So the portion that is dilution. That's just saying that's the BOD contributed by the dilution water. That's all it's saying. And the divided by P here is again just for that wastewater. Only some portion of it is wastewater, and that's where that P is coming into play. Okay, so with that, we have an equation. We will use this whenever we have BOD measurements when we need to account for dilution water. So that gives us these two experiments, right? We've got the BOD 5 for the mixture and the BOD 5 for just the dilution. Okay. And then one thing I'll say here is we saw these terms earlier: dissolved oxygen initial, dissolved oxygen final. And then just to clarify, I don't know if it really helps to relabel it this way, but the book says we'll use the term B to mean the dissolved oxygen initial and final in the dilution. So this is BI, and then eventually B final, where we have dissolved oxygen initial, and then eventually after 5 days, DO final. So that's just, they're just saying dissolved oxygen and just using the term B to label it. Okay, so let's do an example of the problem then. Here we have a test bottle containing just seeded dilution water that has its dissolved oxygen level dropped by 1 milligram per liter in a 5-day test. A 300 milliliter bottle is filled with 15 milliliters of wastewater, and the rest essentially is filled to the rest with that seeded dilution water. You can also say this is a dilution of 1 to 20, right? So one part waste and 20 parts, or the 20 parts total of the mixture. And this bottle experiences a drop of 7.2 milligrams per liter in that same period. And so the question is, what would the 5-day BOD of the waste be? So BOD 5 for the wastewater. And by the way, we could do this for 10 days or 3 days. If we get less than a couple days, then it's probably not going to be very accurate. 5 days is pretty standard, but theoretically you could choose a different day. We're going to keep it at 5 days. I just wanted to make that note. So go ahead and work on this problem. I'll go ahead and remind you here that our equation we derived a moment ago was BOD wastewater, DO initial, DO final. We're going to rewrite it. Actually, you know what I'm going to do? I'm just going to go ahead and come out of this for just a moment, and pardon me, I'm just going to copy paste that equation for you. So just give me a moment. Add it to the slide as a reference. There you go. Okay. So again, take a look. See if you can solve that, and I'll give you a moment to work on that before I do that with you. And if you get a chance, maybe you can tell me if you like the feeling of me pausing for a moment, or if you prefer just pausing on your own. Give me some feedback there. Is it awkward if I just sit here and look at my phone for emails or whatever for a minute, or do you like that? Do you care? Do you guys pause sometimes, rewind or anything? I guess you'll probably tell me in 5 minutes if you pause for 5 minutes, right? Okay, well that's good to know. And if anybody feels differently, let me know. Cool. Okay, so let's work through this together. In some sense, these are pretty straightforward once you understand how the system is working. Okay, so let's take a look at the first bit of information. The seeded dilution water has its dissolved oxygen level dropped by 1 milligram per liter in a 5-day test. And so we don't know how much dissolved oxygen we started with, but we know the drop, so it doesn't really matter too much. So we could, if we wanted to, define the BOD and the dilution. Now, if we use this equation here, we've already got that, right? But let me just write it out to be a little more clear. This is going to be that BI minus B final, and then normally we would have the dilution factor, but we know that it's in that experiment, it's all the dilution water. There's no other things needed. So the BI minus B final, that drop was 1 milligram per liter. It's as if we started with 9 minus 8, right? That's what it's referring to, is it dropped that amount. So instead of finding a specific BI and a specific B final, we can actually just get that term together. So it may actually sometimes be helpful to think of this as BOD D here. And that was, if we look back at our derivation, that's exactly what it showed here. BOD of the D times 1 minus P. Okay, so that was probably maybe one tricky point if you, as you're acclimating to problems of this sort. So that's an important part. Okay, so that means in our overall equation, as we're solving for the BOD of the wastewater, we now have some information there. Let's take a look at the drop for the mixture itself, because again, this is the mixture. That's kind of the experiment that we're really, that includes the wastewater that we're observing. And that experiences a drop of 7.2 milligrams per liter. So the initial minus the final is the amount that dropped, right? So that's going to be 7.2 milligrams per liter minus that 1 milligram per liter. And that really only applies to the portion that was dilution water. So this is going to be times 1 minus P Let's go ahead and find P now that we're here. So P, it says this is a 15 milliliters of wastewater and the rest seeded dilution. So this is going to be 15 divided by 300, which we could probably do off the top of your head, but let's just go ahead and it's 0.05, which is 1 divided by 20, so that gave it to us there too. So P is 0.05. No units there, so we have milligrams and milligrams on top, and then divided by, again, 0.05. So with that, we can solve. And so, yeah, I think the only potentially tricky part was probably understanding the drop. And again, it comes back to kind of the language that a problem uses in acclimating to kind of what it's asking for, understanding that. Okay, so we have 7.2, and let's go ahead and put some parentheses here. 7.2 minus 1 times 0.95. If we do 1 minus 0.05, that gives us 0.95. All of that divided by 0.05. So 125, and the units here are going to be milligrams per liter, BOD 5. Okay, so that gives us an answer here. Now, if you wanted to, you could actually solve for the BOD of this dilution water. And in fact, in a sense, we did. That's actually, we already did that. That's 1 milligram per liter of BOD in that dilution seawater. So it's not a lot of BOD that we're adding, but it's enough to add the bacteria, and maybe it's a little bit variable. So we don't know exactly the amount of BOD. Maybe the bacteria that we have alive and growing because we need to use them as live seed. It's a little bit like adding yeast to bread to make it rise. We need the yeast to be alive, right? How much of that ingredient of the stuff that's allowing them to live and grow, that BOD, how much of that is going to be in there? Well, it's probably variable. Maybe we made a new stock of this bacteria 5 days ago instead of 2 weeks ago, or maybe we need a fresh one, and that means they've consumed more or less of the stuff. So chances are good that particular thing is going to vary. Okay, so next time, and that kind of covers it for the BOD measurements itself. There are a few complexities, a few assumptions, but overall, as you see, it's just a pretty simple algebra. It's just simply, it's knowing what the question is asking for or referring to, and then you're pretty much okay. In terms of understanding what happens to BOD downstream, that's where we want to get into a little bit more depth with modeling and understanding the difference between the dissolved oxygen in the water, like the stuff that's there right now, versus a deficit. So an oxygen deficit, perhaps that has been caused by waste being added to the water, and that BOD has removed the dissolved oxygen. So it's created a deficit. And if the deficit gets too large, that means there's not enough oxygen. Maybe we reach a critical point where we start getting fish kills. This is another fairly common issue with new aquariums. If you end up in a situation where you've gotten your dissolved oxygen too low, maybe you've added too much fish food and there's too many fish and they're all consuming the stuff, making a lot of waste, and then the bacteria are removing the oxygen quicker than it's being added back, right? So that's another potential concern for aquarists, for example. So this is where we're going to pick up next time. I just have one set of slides here, and I kind of just put it all in one. So I've posted this particular slide set to Moodle. I'll update it again after next lecture when we fill it out further. But essentially what we're going to do is consider rivers and streams in particular, and they kind of act like a plug flow reactor, right? So we can imagine a stream or river might meander and stuff, but chances are, we're not getting mixing of water from here to here. Maybe we'll get mixing here, but on a larger scale, it would be maybe just a less ideal plug flow reactor. And for our purposes, we might as well assume it's a plug flow reactor. That's going to give us the best approximation. So with that in mind, it'll look a lot like a batch reactor over time. And again, if you think about water traveling through a river over time is essentially equivalent to distance of travel if you have a constant velocity, which, again, it's an assumption. It's not entirely true, but it's a useful and simple assumption to make. So we can know how far down the river the dissolved oxygen is going to, or the deficit is going to be a problem. And the point here is going to be we're going to map at what point do we reach a deficit and how bad is that deficit. So if we look at dissolved oxygen in the water over time, that's kind of what we're looking for, is that critical point at the lowest, and maybe the dynamics of how it exists. Now it might be that the river is always a little bit of a deficit if this is our dissolved oxygen saturation at a given temperature. Chances are good natural processes are creating a little bit of a deficit, and then when we add wastewater, it's going to take some time. We will have an oxygen demand, and then eventually we're going to have that coming back up towards kind of the natural state. So that's where we're heading next lecture, and I think that's all we'll do for today. So again, please do fill out the survey. I will aim to have a Kahoot or similar kind of feedback. Maybe I'll put it into a quiz. Maybe I'll keep it for anybody that's attending live. I want all your feedback, so I'm not meaning to keep that for only the people who are live. Maybe I'll do that to get a little more engagement in class next time. It's kind of fun to see live feedback and do the Kahoot thing, but also add something online for Moodle. Okay, so anyway, I appreciate the feedback. It's going to help me in the future, even if it's just carrying this type of teaching forward into more hybrid, in-person primarily mode. So with that, have a good day. Try to stay dry, and I'll see you on Thursday. I'll hang out a moment if there are any questions. Okay, what was the answer for example? Yeah, it was 125 milligrams per liter. So if we take 7.2 minus, essentially it's like 7.2 kind of minus 1, because 1 times 0.95 there is about 1. It's 0.95, right? So 7.2 minus 0.95 is like 6 point something, and then we divide that by 0.05. That's essentially multiplying by 20, and it's kind of like 6 times 20 or thereabouts, and it turns out that's 125. No problem. All right, so thanks for joining me, or tuning in later. So we'll see you on Thursday.